to record that part, did I? And you don't need to see me, so I'll turn off the webcam and then we'll go. That is true, isn't it? There we go. Okay. Okay. Oh, I didn't actually share that, did I? That was okay. That was the picture. Okay, so let's get back to the subject of concavity. Okay, so I realized this is sort of the more elaborate slide than the one that I had actually put up the other day. I thought this might be a little bit easier to see. There we go. Okay, so here is, all right, so the definition of concavity is essentially we say that the function is concave up if its first derivative is increasing on the interval AB, and it's concave down if its first derivative is decreasing on the interval AB. So when you think of concave up, what you're really thinking of is a function that's kind of smiling up, or it's like a bowl upward. And if you think of a function that's concave down, you're thinking of more of a frown, like the one that you see on the right side. Now, the way that we describe this analytically is we say that, as we say that what's happening on the left is that the derivative is actually increasing. We start, if you look at the red lines, we have a tangent line that's very, very steeply negative, which I just estimated at -10. Then over here, it becomes somewhat less steeply negative. Let me see if you can still see what I'm pointing at, or is it not pointing? I'm trying to see if the pointer is working. Not exactly. Okay. All right. So anyway, I'll just have to narrate what it is. So the point is that the slopes go from -10 to -1 to 0 to 1 to 10. That's an increasing first derivative, and the way it shows up in the graph is it looks like an upward pointing sort of bowl, and we call that concave up. If instead we go in the other direction, like down here, where we go from a slope that's high into one that's low, 10 down to -10, we get something that looks more like a frown and is pointing downward. So where is this? Okay, that's why I can't do that. Sorry, I just wanted to see one thing. Yeah, okay. So what that does is it suggests yes, it has. So what that does is it suggests something called the second derivative test. The second derivative test is another way of determining whether a critical number is a local min or a local max. We already saw the first derivative test, where basically what we're doing is we're looking to see if the function is increasing to the left of a critical number, decreasing to the right, and if the first derivative test, we said that if the function is increasing to the left of the critical number, decreasing to the right, then it's a max. If we have the opposite situation, then it's a min. What the second derivative test is, instead, by looking at the second derivative, it's able to tell us whether the function is concave up or concave down. This reminds me, I forgot to point something out. Since I forgot if I had mentioned this the other day, but since the definition of concavity is that the function is concave up if its first derivative is increasing, then what that means is that we're looking for the first derivative of the first derivative to be greater than 0. So that means, and of course, the first derivative of the first derivative is just the second derivative. So concave up is detected by the second derivative being greater than 0. Concave down is directed by the second derivative being less than 0. So going back to the second derivative test, what we can do is we can detect, for example, that this point is a local max by looking at whether it sits on top of a portion of the function that is concave down, or this one could be identified as a local min because it's sitting on the bottom of the portion of the function that's concave up. So what we can do is we can determine this by looking at the critical point and plugging it into the second derivative and simply asking whether the second derivative is positive or negative. In the case where the second derivative is positive, that's the situation you see on the right, where we have a concave up function, and its local min is have a concave up function. So what we would get is here that f. Let me give these numbers. This is called that C2, and that's C1. So here we would say f prime prime of C2 is greater than 0 because it's sitting at the bottom of a function that's concave up. If it's greater than 0, then we identify C as the location of a local minimum. And in the opposite situation here, for example, where we have f prime prime of C1 is less than 0, we have it sitting on top of a concave down function, we would say that f of c is a local maximum. So this is just another way of detecting whether whether the critical number is a min or a max. The only issue that doesn't apply in the case of the first derivative test is that we might get the third situation where we get the second derivative is 0, in which case it's not that the answer is neither a min or max, but rather the second derivative test is inconclusive. And if that happens, then we just have to go back to the first derivative test. So the second derivative test is usually easier to apply when it works, but sometimes it doesn't work. And then you have to go back to the first derivative test. Okay. So any questions about that point? Okay. 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 Then we have this concept of an inflection point, which is the point where the concavity changes from up to down or down to up. So what we know is that the changes in concavity are going to occur at one of two types of points. One of them, one of the types of points where change in concavity occurs is like here. I want to use a less alarming color, is where the second derivative is 0. The other type of point is where the second derivative doesn't exist. As you recall, the two types of places where a function can change from increasing to decreasing, or vice versa, is where its first derivative is 0 or doesn't exist. And we gave those kinds of points the name critical numbers or critical points. Some textbooks refer to places where the second derivative is 0 or doesn't exist as a second order critical number. I don't believe our textbook, I was looking for that term and I didn't see that in the textbook we're using. So this is just kind of an unnamed concept. It's just a place where, it's a place where concavity might change, but unlike critical points, it doesn't really give it a name. At least I didn't see one in there for it. So you just kind of have to remember the concept. So what we're looking for here when we look for changes in concavity, we could be looking for something like this. This is an example of a function you've all seen. It's y equals x cubed. And as you can see, it's concave up in that part of the function. It's concave down in that part of the function. So we would call this an inflection point. There are other examples of this. This is kind of a case where the function flattens out, but you don't always have that. You may have something more like this. Actually, let me draw it like this. There we go. So we probably call that an inflection point. And if you notice, this function is increasing even across its inflection point. So increasing or decreasing really has nothing to do with concave up or concave down. A function can be increasing and concave up or increasing and concave down. Here we clearly have the concave up part, and here we have the concave down part. So these are just really two different shapes of increasing functions. And the point where we change from positive to negative, we just call that an inflection point. So positive, when we change from up concavity to down concavity, rather, we call it an inflection point. Okay. So any questions about that definition before I just move on to an example? Okay. Let's see. Okay. Okay, so here's just an example. Find inflection points and intervals of concavity of this given function. So what we would do here is we'd simply find the second derivative, which we do first by finding the first derivative. So the first derivative is 15x to the fourth minus 20x cubed. And the second derivative is then 60x cubed minus 60x squared, which equals 60x squared x minus 1. Isn't it nice how textbook examples always come out so clean? That's why they call them textbook examples. So, all right, so what we can see is that f prime prime, it doesn't have any does not exist points. There's no place. F prime prime is just a polynomial function. It doesn't have any places where it doesn't exist. So all we have to do is look for the places where it's 0. You can say f prime prime of x equals 0 at x equals 0 or 1. So those are the places where concavity might change. We don't know that it does. We have to actually check that it does. I'm just going to draw those on a number line. So we see that we have here 0 and 1. And the places where I'm going to look for the places where I'm going to test the function. I'm going to test f double prime to see if it's positive or negative. I'm just going to pick arbitrary points on either side of these critical numbers. So I need to pick one here. That's going to be -1. I'm not drawing this to scale. I'm going to pick 2, and then I need to pick 1 in between the critical numbers. So this is really like the same thing we did with the first derivative test. You can pick any value of x as long as it's between the critical numbers. Well, here you can pick any value of x as long as it's between the candidate points, the places where f double prime is either 0 or doesn't exist. So now I'm just going to plug in points in red. F of -1 is equal to 60 times -1 squared times -1 minus 1. So that comes out to 60 times -2, which is -120. F of 1/2, I've already calculated these in advance. I know you could plug in numbers. So this is actually going to be -15 over 2. And f of 2 is equal to 240. So the important point here really is not so much what the numbers are. We'll actually make use of the value of the second derivative when you get to Calc 2. But for now, the only important point about the second derivative is whether it's positive or negative. So we can see that we have negative and positive. So what that's telling us is that there is a change in concavity. Let me put them here. So this is going to be negative, negative, and positive. So there is actually a change in concavity across the number 1, but not across the number 0. So what we would say is that x equals 1 is location of an inflection point. And we could also say f is concave down on negative infinity 0 and 0, 1, and it's concave up on the interval 1, infinity. X equals 1 is inflection point. So that's the answer. Okay. Oh, sorry. Yes, that. Thank you, Maria. These should have been f double prime. Is it not an inflection point because it was x squared? I'm not sure what you mean. I'm sorry, could you clarify the question, Andrew? So that's the part of, okay, so I see what you're saying. So you're saying, does it have anything to do with the fact that the part of the expression for f double prime that gives the solution x equals 0 is the x squared? That really has nothing to do with whether it's an inflection point or not. The only requirement for an inflection point is that concavity changes across the point. So, had we gotten a function where had we gotten a function where somehow the second derivative was positive to the left of 0 and negative to the right of 0, or vice versa, then 0 would be an inflection point. The fact that it's 0, that there's an x squared, which causes you to have the same sign on both sides, doesn't really that doesn't really force it. That doesn't necessarily force it to be true. There are situations where you could still get, depending on how you factor it, you could get one on either side or the other. I see what you're saying, but I just don't really think about it that way. So, okay. Let's see. Okay, so let's just do a second derivative test example. Okay, so let's analyze the critical points of this function. A little more space. Let's analyze the critical points of f of x equals 2x minus x squared times e to the x. So what we need to do is, first of all, we need to find the critical points. So we're going to find f prime of x. And just using the product rule, because this is in fact the product of two functions, this is going to be 2x minus x squared e to the x, and then plus 2 minus 2x e to the x. So that's the product rule, and that comes out to e to the x, 2x minus x squared plus 2 minus 2x equals 2 minus x squared e to the x. So that's the derivative of this function. What we need to do is look for, first of all, there is no place where this function is undefined. I'm looking now at the derivative function. This expression is certainly defined every place, so there are no points where the derivative doesn't exist. All we have to do is look for places where the derivative is 0. You know, e to the x is never 0. E to the x is always a positive function. And 2 minus x squared is going to be 0 where x equals plus or minus root 2. So let's say that f prime of x equals 0 when x equals plus or minus the square root of 2. So plus and minus root 2 are critical numbers. So we found the critical numbers. And now what we can do is we can use the second derivative test to classify these critical numbers. So let's find the second derivative. Prime of x. Again, using the product rule on the first derivative, that gives us 2 minus x squared e to the x, and then plus negative 2x e to the x. So that equals e to the x 2 minus x squared minus 2x. So that's the function for the second derivative. Now we can plug in the critical numbers. Plug them into f prime prime of x. So f prime prime of the square root of 2 is equal to e to the square root of 2. And that's going to give us 2 minus the square root of 2 squared is just 2. And then 2 times the square root of 2 is 2 root 2. Now, you don't actually have to find what that value is. I know that everybody's, wants to say, oh, well, let me get out my calculator and plug it in. It doesn't really matter what it is. The important point is that we have here e to the root 2, which is a positive number. And then we have 2 minus 2, which is 0, and then minus some positive number. So we're going to get a number that's less than 0, and that's all that really matters here. And then we can do the same with negative root 2. So that equals e to the negative root 2. And we get here once again 2 minus 2. And then we're going to have minus 2 times negative root 2. So that comes out to plus 2 root 2. And e to the negative root 2 is still a positive number. And then in parentheses, we have a positive number. So that's going to be greater than 0. So what that tells us is that root 2, let's see, the second derivative test tells us that root 2 is sitting at the top of what is a concave down function. We know the function is concave down root 2. How do we know that? Because its second derivative is negative. So what that means is that we have a concave down function and point is sitting right on top of it. So root 2, or rather I should say it this way. This is how I should say it. F of root 2 is a local max. And then for the opposite reason, where we have negative root 2, that's saying is the function is concave up, so negative root 2 is sitting down there at the bottom of a concave up function. We can say f of negative root 2 is a local min. So there's the second derivative test. Okay. Anyone have questions about that? Let's see. I'll show a couple of other examples. Some of these are a little bit weird. Do this one first. I'll just wait for the question. Oh. We have to use the second derivative test, or can we just find the values to the left and right on an exam? I mean, really both types of questions could apply. I might ask you specifically to write out a second derivative test solution. In most cases, it's kind of at your option. My view of the second derivative test is that it's usually easier to use. So, sweet. Yeah. What Jeff said is correct. If you think about it, if you can find the second derivative very easily, then it's going to be easier because you only have to calculate one value. You don't have to choose. You may have to, in order to apply the first derivative test, you might have to choose some fractional value in between two integers. It may just be easier to use the second derivative test. So that's why you might want to use it. So, okay. So first of all, I want to just give an example where the second derivative test is inconclusive. This is kind of the classic example of that. It's a little easier than the ones in the textbook. Here we have f prime of x is equal to 4x cubed, and f double prime of x is equal to 12x squared. So what we can do is, first of all, find the critical numbers. F. So the critical numbers of f, we're looking for places where the first derivative is equal to 0. Obviously, there's no place that f prime is undefined. So we're looking for 4x cubed equals 0, which only happens at x equals 0. So 0 is the only critical number. Okay, so what we can do is we can try to apply the second derivative test. So f prime prime of 0, which is 12 times 0 squared, which is 0. Well, if you recall, a second derivative test when you get a second derivative is 0, the test is inconclusive. That doesn't mean that it's neither a local min or a local max. Just means the second derivative test doesn't tell you the answer. So the only thing you can really do is just go back to the first derivative test in this case. Let's go back to the first derivative test. We go back to the first derivative test, and here's our critical number 0. What we want to do is pick values to the right and left. Easiest values to the right and left to pick are going to be 1 and -1. So let's perform that. Let's get f prime of 1 is equal to 4 times 1 cubed, which equals 4, and f prime of negative 1 equals 4 times negative 1 cubed, which equals negative 4. So what we have is on the right side, values of f prime, sorry, on the left side of 0, we have negative, and on the right side of 0, we have positive. We know what that looks like. We have a function that's going downward and then upward. So that means that x equals 0, or rather I should say it this way, say it the way the book says it. F of 0 is a local min of f of x equals x to the 4th. Now, what's going on here? How can it be that we have a min, but the second derivative test was inconclusive? If I draw the function, it probably becomes a little bit more clear. Y equals x to the 4th looks sort of like this. I'm kind of exaggerating here what it looks like, but it looks very much like y equals x squared, but it's not a parabola. Parabola is a term specifically reserved for the graph of a quadratic function. Function that has a 4th degree power is actually called a quartic function, Q-U-A-R-T-I-C. And y equals x to the 4th just happens to flatten out so much at the bottom. It's a U-shaped function like a parabola, but it's kind of a different U-shaped. It's much flatter at the bottom. It flattens out so much that just for a split second, like right at this point here, it has no concavity at all. So the function is concave up here, and it is concave up here, and clearly it's decreasing down to 0 and increasing away from 0. It's just that it has no detectable concavity at 0, and that's why the second derivative test fails at that point. So this is just an example of a situation where you actually have a min, but you cannot detect it through the second derivative test. Okay. So any questions about that example? Okay. Let me just give you another example, another kind of weird case that exists. There we go. That's a good one. Let's find the points of inflection of y equals x to the 5/3. The thing about y equals x to the 5, f of x equals x to the 5/3. So the thing about this example is that if I find first derivative, I'm going to get 5/3 x to the 2/3 just by the regular power rule. And then the second derivative, applying the power rule again, 2/3 times 5/3 is 10/3. Sorry, it's 10/9 rather. And then subtract 1 from the exponent. 2/3 minus a 1 is negative 1/3. So it's not quite clear just from looking at it that way, although at a certain point you should start to recognize this. This is equal to 10 over 9 times cube root of x. So when I write it in that form, it may become more clear that you can't have x equals 0 because you're going to have division by 0. So here we have is f prime prime is undefined at x equals 0. So this is the other reason, the one we don't really think about that much, where we'd have to consider a possibility that an inflection point is a place where the second derivative is undefined. Remember, we're going to look at places where f prime prime of x equals 0, or 2 f prime prime of x does not exist. In other words, these are sort of candidate points for, these are candidate points for inflection points. If you think of them as candidate points, you can kind of think of f prime prime of x equals 0 as the Joe Biden of inflection points, and f prime prime of x does not exist as the Bernie Sanders of inflection points. So that's waiting for the comment. I just say these things just to see who's listening to me. Okay. So anyway, I'll have to send that to the campaign and see what they think of that. They'll go, what? Inflection points? So anyway. So, all right. So we know that x equals 0 is sort of a potential inflection point. We just have to see if it is. We test it in the same way. We can test x equals 0 like any other candidate inflection point. So let's just pick arbitrary points on either side. That, and we'll just calculate f prime prime of 1 is going to be 10 over 9 times the cube root of 1, which is 10/9, and f prime prime of -1 is 10 over 9 times cube root of -1, which is -10 over 9. So okay, so here we have 10. Okay, so on this side we have negative concavity, and on this side we have positive or up concavity. So what that means is that it is true that x equals 0 is an inflection point. In other words, it is a place where concavity changes. And what this function actually looks sort of like this. So this is y equals x to the 5/3. And as you can see, I have down concavity there, and I have up concavity there. I'm just letting someone type a question. Oh, why are we plugging them into the second derivative and not the first? Yeah, I realize it gets a little confusing. When we're performing the first derivative test, we would be plugging points on we would be plugging numbers on opposite sides of a critical number into the first derivative, because we try to see if the function is changing from increasing to decreasing. When we're looking for inflection points, we're looking for something a little bit different. If you notice, this function never changes from increasing to decreasing. It's increasing all the way from the left to the right. What we're looking is to see where it changes its curvature. In other words, where it changes its concavity. And clearly, on the left, what we have is a function that's pointing bowl down, and on the right, pointing bowl up. And that's the thing that we can detect through the second derivative as opposed to the first. They're just different aspects of the shape of the function. Okay. All right, because I want to get to this topic. I have a couple, if time permits, I have some other examples that are different, mainly because they're algebra. I'd rather, I think, make sure that I have enough time to do some graph sketching examples. So, so what we're doing really is we've been talking about the shapes of curves in terms of their derivatives. So in other words, been saying that slide. What I've been saying really is that these are some shapes that we can associate with derivatives that we know. So an increasing function, which looks like this, we can detect because its first derivative is greater than 0. A decreasing function, which looks like that, we can detect because its first derivative is less than 0. And then we have a concave up function, which looks like this, and we can detect that because its second derivative is greater than 0. And then similarly, concave down is going to look like that, and the sign that shows up is that the second derivative is less than 0. So what we've been doing is we've basically been given a function and said, well, tell us which of these apply by looking at its derivatives. The sort of next level of this is, what if I give you information about the derivatives? Either I give you the derivatives themselves, or I just tell you where the derivatives are positive and negative. The question is, can you draw something that looks sort of like the function? I realize that task itself freaks a lot of people out because they say, well, why can't I just draw the actual function? Someone actually asked in the last class, the class this morning, they said, well, can't I just take out a graphing calculator and draw the function? Well, you can, it works. It's just a different sort of task. This is the exercise as we get to, this is going to be section 4.6, is basically going to be to try to draw the function from, from knowledge of what its derivatives are. This is where actually the shape of functions becomes important. And of course, as I sort of alluded to before, this is actually, this is actually kind of timely, because we've talked about, we've talked about in the news a lot, is this bending of the curve that I'm sure you've heard of. So what I've put here is, this is the case where it becomes very important as to whether you write the L or not in the word, because what we have here is I'm graphing number of infections, not inflections, against time. So here we have, I don't know which country this is, but if you, what do you mean hidden? That's, so if, anyway, if you imagine this as being March 1st over here and March 30th, this is roughly what we've been seeing in the world today. So we've been talking about the bending of the curve. Is here, if you notice, right up to this point, the infections look almost like they're growing exponentially. But by keeping people really far apart from each other, we can keep the infections from growing exponentially, and then you start to get a curve that goes in this direction. And notice that even though, obviously we'd like to get down to this point here where the infections are actually dropping, at the very least, once we hit this point, we can say that instead of the infections going up at that rate, they're going up at that rate. So we're changing the rate at which infections are increasing. And that happens at the inflection point there. So, so this is actually quite a timely topic. Now, I don't claim that calculus has an answer to the predicament that we find ourselves in now. And that's quite rare for me because, as you know, I think calculus has the answer for everything, but I'm not sure it has the answer for this. However, it does at least give us a way to understand the diagrams that we've been seeing in the news. So let's go back to graph sketching. Okay. Oops, sorry. There we go. I wanted to draw this for you rather than use the previous classes. Okay. So we have, okay, so, sorry. As we've seen, the notion of something being increasing and concave up, these are totally independent of each other. So really you have to think of these, of the shapes of the curves as being sort of combinations of increasing and concave up, a combination of monotonicity and concavity, where monotonicity refers to whether the function is increasing or decreasing, and concavity refers to whether it's concave up or concave down. So there are really four combinations, and they look like this. Increasing and concave up would be shaped like this. Here's an increasing function, and you can see that it's concave up like that. If instead I have increasing and concave down, here I have a function that's increasing. It's still increasing, but its concavity is pointing the other way. And then decreasing works the same way. I have decreasing and concave up, looks like that. And decreasing and concave down looks like that. So by looking at the combination of monotonicity and concavity, we can get an idea of what the shape of the function is, and we should be able to sketch it from that information. So in order to do that, we just need one more term, which is really just kind of a combination of the other terms that we've seen. But actually, let me just ask, since this picture is kind of new, does anybody have any questions about what I've drawn here and what this chart means? Okay, good. So okay, so let's just define the term transition point, which is really just kind of an aggregator for places where f prime equals 0 or f prime does not exist. In other words, what we're calling critical numbers, or this sort of unnamed concept of f prime prime equals 0 or f prime prime does not exist. In other words, these are the places where the function is actually going to change its shape. Places where one or both of these things is true. So we're going to call these transition points because they're places where there's going to be a transition between the shape in the shape of the graph. So those are the places that we're actually going to look for before we start to sketch the graph, and then we're going to analyze whether the first derivative is positive or negative on either sides of those transition points, and that's going to allow us basically to pick one of these shapes as the shape to draw for that interval of the graph. And that's anyway, that's what we're going to do. So let's see. Here's the process of how to sketch the graph of a function. First thing you do is you find the first and second derivatives if they're not given to you in the problem. Sometimes I'll just give them to you in the problem because frankly, it's a real mess to grade a problem if I say find the first and second derivative and you do them wrong and then you do everything right based on the wrong derivatives and you get the wrong graph, but you did it, it's just a mess to do that. So it's kind of easier, unless it's a really easy derivative to find, if I just tell you what the derivatives are. So next thing you do is you find the critical numbers, the places where f prime is 0 or undefined, and then you also find the places where f prime prime is 0 or undefined. That's steps 1 and 2. For number 3, what you want to do is really determine whether the points that you found in 2 are local mins or maxes or inflection points, because what that's going to do is it's going to tell you when you have to change from increasing to decreasing, or when you have to change concavity of the function, or when you have to change the concavity of the function. So once you do that, you're just going to draw in the appropriate arcs, by which I mean you're going to draw in these shapes in the appropriate intervals Or you may even, if you identify something as a max, you can just draw like a little arc like that over the max. Or if it's a min, you can draw something like that. So you're just going to draw them in based on the information that you have and what we already know about the shapes of functions. So let's see. I'll let you ponder this for a minute just while I talk. One of the things that's kind of unfortunate about this topic, especially when I teach Calc 1 in the fall, which I did not, is that one of the things that happens, you may not have noticed this, but there's always like some older professor sitting in your class sometime around mid-November. That's because professors get observed by their departments in mid-November. And it seems to me that our schedule for reviewing people is always such that they do it during the graph sketching unit. And the problem with the graph sketching unit is just that the problems are so long and tedious. And I'm like, oh, why can't I demonstrate something when the topic is actually more interesting to see? Fortunately, I was teaching only Calculus 2 this fall, and the review period comes up right in the middle of Taylor's series, which is the most interesting topic in Calculus 2. So I got a little bit redeemed there. But anyway, I'm looking at what Jeff is writing. Yeah, that's correct. That's just the way it works. So anyway, let us. Okay, so let's sketch the graph of an exotic polynomial function. And exotic, by the way, is not. It's not like it's a term of art. It doesn't. When I say it's exotic, I just mean that this is a polynomial that you probably don't automatically know what the graph of it looks like. So we're going to sketch this just using the techniques that I've just described. Now, the thing that I have to warn you about is that these problems always take an enormous amount of paper. I've actually reserved for myself a couple of work pages just to do the calculations on these. They just take forever to do, and that's why we can only do a small number of them. But fortunately, you can see most of the techniques just through one or two problems. Okay, so let me just turn to the next page. We'll do the work, and then we'll come back and draw the graph on this page. All right. So the first thing we need to do is we need to find first and second derivatives. So we have, recall that f of x was equal to 3x to the fourth minus 8x cubed plus 6x squared plus 1. So f prime equal to 12x cubed minus 24x squared plus 12x, which equals 12x x squared minus 2x plus 1, conveniently equals 12x x minus 1 squared. And f double prime of x is going to equal, I'm just going to use that form of the derivative because that's the easiest one to get to differentiate. So that's going to be 36x squared minus 48x plus 12, which equals 12 3x squared minus 4x plus 1, which equals 12. Let's factor that in my head. 3x minus 1, x minus 1. So what you can see is that, first of all, neither of these derivatives is going to have any place where it's undefined, but they both have two places where they're 0. So f prime of x equals 0 implies that x equals 0 or 1. Those are the two places where this expression is 0. And f double prime of x equals 0 that gives us That's going to be true where x equals 1/3 or 1. So I should have pointed out here what I'm doing. I'm finding transition points. So we can see what the 3 transition points are. Transition points are 0, 1/3, and 1. So these are the places where we're going to watch for changes in monotonicity or concavity. The truth is, we really only have to watch for changes in concavity at 1/3 and 1, because we've seen that f double prime does not change sign at 0. And similarly, we don't have to watch for changes in monotonicity at 1/3, because 1/3 is not a critical point. It's not going to change from increasing to decreasing or vice versa at that point. Okay. So I found the transition points. Let's turn the page. Find local mins, maxes, and inflection points. Okay. So first of all, the x equals 0 and 1 are the critical numbers. So we want to determine if these are local mins, local maxes, or neither. So first thing we can do is we can use the second derivative test. We can at least try it on these points. So recall that f double prime of x was equal to I just need to remind myself of what that was. F double prime of x is 12, 3x minus 1, x minus 1. So let's plug in the 2 critical numbers. F double prime of 0 is going to equal 12 times -1 times -1, which is 12. And f double prime of 1 is going to equal 12 times 3 minus 1, which is 2, and 1 minus 1, which is 0, which is 0. So this positive concavity, this is going to be a min. In other words, I realize that sort of sounds sort of backwards. You get a positive number in the second derivative, and it means the point is a minimum, but just keep in mind what the picture is. We're saying is concavity is positive, and that point is sitting right at the bottom there. For x equals 1, we get an inconclusive result with the second derivative test. So we really just have to go to the first derivative test. Let me just draw all the transition points here. It's going to be 0, 1/3, and 1. I'm not really drawing it to scale. What I'm going to draw here is I want to test the point 1. So I'm going to put in 1/2 and 2. I'm just going to pick 2 points on either side of 1. And let's see. Let's go to the first derivative test. First derivative was 12x minus 1 squared. So what I'm going to do is I'm going to plug in these two red numbers, 1/2 and I'm going to plug in 1/2 and 2. So f prime of 1/2 is going to equal 12 times 1/2 times 1/2 minus 1 squared comes out to 6 times 1/4, which is 3/2. And f prime of 2 gives us 12 times 2 times 2 minus 1 squared, which is 24. It doesn't really matter what the numbers are. The point is they're both positive. We never change sign across the critical number 1. So what we can conclude here is that f of 0 is a min, and f of 1 is neither min nor max. So that's what we can conclude about those points. Okay, so that's what we know about whether the functions are increasing or decreasing and what's a local min and what's a local max. What we now need to do is find r equals 0, sorry, x equals, were they 1/3 and x equals 1 inflection points. And what we want to do is we want to just test values that are, we just want to test values that are in between these points to see, sorry, on either side of these points or between them to see whether concavity is changing from positive to negative or vice versa. So I'm going to choose, points that I'm going to choose are 0. I'm going to choose, I'll use 1/2 and 2. So recall that I'm only checking these points because these are the only places where concavity can potentially change. There was no indication that concavity was going to change at 0 because the second derivative was not 0 at x equals 0. Go back for a minute, just so you know what I'm talking about. What we found was that f prime prime was 0 at x equals 1/3 or 1. There was never a possibility that at x equals 0, concavity was going to change from positive to negative because the second derivative is not 0 there and is not undefined. So let's just plug in these values. So I have f of 0, use better color than that, f of 0, sorry, f double prime of 0 equal to we already calculated that, so that's going to be 12 times -1 times -1, which is 12, and that's positive. F double prime of 1/2 equal to 12 times 3/2 minus 1 times 1/2 minus 1, which was 12 times 1/2 times negative 1/2, or negative 12 over 4, which is negative 3. That's negative. And then f prime prime of 2 is 12 times, that's 3 times 2 is 6, minus 1 is 5. Sorry. 1 and 2 minus 1. So that gives us 12 times 5 times 1, which is 60. So if here, that's negative and that's positive. So we actually do have a change in concavity across both of these points, both 1/3 and 1. You know, there actually is a third derivative. I mean, you could do it that way because essentially what you're doing is you're asking whether at that point the you are actually asking. I mean, you actually are asking whether the concavity is decreasing at that point. So you could do that by checking whether the third derivative is less than 0. We just don't really teach it that way, but that's not an unreasonable observation. Anyway, I just want to finish this up because it looks like I'm about to run out of time. So let's go back to here. We have 0, 1/3, and 1. So what I want to do, right, f prime, 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 and I'm simply going to mark off all the transition points. Now, I just don't want to keep flipping back and forth between pages, so I'm just going to keep in mind what we found. What we found was that this point was a minimum. If it's a minimum, then that means that it must have been decreasing into that point. So we must have gotten negative first derivative there and a positive first derivative here, because that's what it means for it to be a minimum. It means that it's negative on one side and positive on the other. We also saw that the function was still increasing there, and it was still increasing here. So we had positive first derivatives. And then here we had concave up. Second derivative was positive there, and it's still positive there. It was negative here, and it was positive here. And we also know that because of what the function is, we can see that if we plug in f of 0, we're just going to get, in this color, we're going to get that point at 1. So we have a minimum here. We have a function that's going to be increasing up to here, and then it remains increasing, but is concave down, and then it's increasing again. So here I have an inflection point, and here I also have an inflection point. And also, just looking at this function, I know we covered this in chapter 2, but if we imagine the function, going all the way out to negative infinity and positive infinity, we see that this 3x to the 4th is just going to keep growing to positive infinity. So we can sort of draw this as going out toward positive infinity like that. So I have here a min and 2 inflection points, and that's the graph of this function. Would have grokked out based on what its derivatives are equal to. So you can see those problems are really exhausting. I know I'm a minute over. So thanks everyone for being here. I'll stick around for some questions afterwards, but I know some of you are going to be rushing across the courtyard to a workshop. You're welcome.